Salinity. Salinity is a scalar state variable of the ocean, and we can measure, observe it, estimate it. Normally we write salinity with a capital letter S. And salinity, being a scalar property, is a function of space, coordinate system x, y, z, and time. Why is it useful to measure, observe, model salinity? The primary reason is probably in estimating density. The density of the ocean influences the dynamics, and it's difficult to directly measure density, so the way it's done is by measuring the key components that can determine the density, and that is the salinity, the temperature, and the pressure. These can be measured in situ, and in this snippet we'll be discussing salinity. The second reason is tracing water masses. There are large swaths of the ocean where salinity varies quite slowly, and in those we can track a particular water mass and even estimate the mixing between two or more water masses by looking at the salinity and how it changes over time. A third reason is survival and habitat. Many of the marine species have a particular salinity range in which they live, in which they can tolerate. Particularly in larval fish, we can examine the survival as a function of salinity. And this is important for fish that live along the coast where salinity can vary rapidly. Salinity can be measured in a number of ways. We can make rapid in situ measurements using the conductivity, the influence of salinity on conductivity. So salinity is really a measure of the amount of salts contained within a sample of seawater. Here we see a graph showing the chloride concentration versus the conductance in microsiemens. So conductance is just an inverse of resistance, so it's an inverse ohm. And we can see that conductance increases for a given temperature. Conductance increases with the amount of salts that are in the solution. So by measuring the conductivity of the fluid, we can then get at, in a fairly complex way, we can get at the salinity of the water. This shows a seabird conductivity, depth, and temperature measurement. You might lower over the side of a boat, and it has a conductivity measuring device here where seawater is pumped through there. The conductivity of the fluid is measured and stored and converted into salinity using a temperature adjustment. There are a lot of different salinity scales and units, and things can be quite confusing. The strict definition is that it's the grams, the amount of dissolved salts in grams per kilogram. And in most of the ocean, the ratios of the salts, the chemicals making up the salts, is roughly constant. But it's not exactly constant. And so in the early 1800s, they just used these constant ratios. They'd measure just one of them, chlorine, and use the constant ratios to determine the total amount of salts and convert that to the salinity. This is a very slow method because you actually have to extract the chlorine from the seawater sample. Electrical conductivity allows you to use conductivity as a proxy. So K is measured. It's a proxy for salinity, and using a complex relation you can derive S. The early basis was based on the constant ratio assumption, but as the precision of these start to increase, the errors were dominated by problems with that assumption, where the salt ratios start to vary from some kind of nominal ratio relationship. And so over the years there have been some better developments, the two big ones being in 1978, the convention of the practical salinity scale, which is based on conductivity. And the important thing is really the precision of salinity is necessary for the purpose of computing density. So if the whole goal is to gather a measure of salinity that can be used for accurately computing small variations in density, that is ultimately the goal. So that was the basis of the practical salinity scale, to come up with a method, a completely conductivity-based method that would allow the determination of a salinity scale that would be useful for deriving very precise values of the density. That is the PSU, and it has no dimensions, and it was used for about 30 years and is now being slowly replaced with the TOS-10, which has a complete thermodynamic basis. It's also known as the absolute salinity scale, and essentially it incorporates conductivity as well as local variations in relationships between conductivities and the salts and the implications on salinity and density. The units of that are denoted SA, and it is not unitless. It is in fact true grams per kilogram. Now, salinity can be measured in situ by using a conductivity sensor, which you can mount permanently on a mooring or drop up and down to get profile measurements or Toyo measurements. Starting in the late 2000s, or the late first decade of this century, we have two instruments in orbit, one from the European Space Agency and one from our own NASA, which are attempting to and successfully measuring salinity from space. These use principles that are similar to sea surface temperature, in that the surface of the Earth emits microwaves and other radiation into space, and these can be measured and used to estimate various things, including precipitation, temperature, and here salinity. The measurements are not as accurate as they are for temperature, but they still are giving now an entire picture of the global sea surface salinity that was never available prior to this. Timescale is about a month, closer to a week. The accuracy is about 0.2 grams per kilogram. The resolution is around 10 kilometers. And there's an example here where you can go and get some snapshots. This is actually an image from our NASA's Aquarius satellite. You can see some of the key features in the ocean salinity here, such as the runoff, the low salinity water coming from the Amazon River, the low salinity water, pocket of water here, where you have meltwater from the Arctic descending along the northeast of North America, even down into our Bay of Fundy. And you have areas of higher salinity in the mid-ocean regions where evaporation exceeds precipitation. The sea surface salinity varies over the year and varies spatially. Depends strongly on various processes such as rainfall versus precipitation. Rainfall tends to decrease the salinity locally at the sea surface because you're introducing fresh water. Evaporation tends to increase the salinity. As the water is evaporated, it leaves behind its salts. And so that process represents a balance at the surface that dominates a lot of the sea surface salinity. We also have introduction at the boundaries in the form of rivers or river discharge, which tends to reduce the coast's salinity near the coast. And you have places with fresher water near where ice is formed as well, depending upon the time of year. And so this picture shows a typical distribution. We have areas where precipitation exceeds evaporation, where evaporation exceeds precipitation. We have areas, as I mentioned, this fresher water, bolus coming down from the Arctic melt, from the Amazon and other river discharges. You have areas of very high salinity. You can see them here. They're red, such as the Mediterranean Sea, where evaporation exceeds precipitation. The Red Sea, where evaporation also exceeds precipitation. These are places where they have hot, dry winds that essentially they easily evaporate the water, leaving the salts behind. If we look at cross-section of the planet from the South Pole to the North Pole, So this is a latitudinal variation of salinity. We can see that the variations in salinity in this plot correspond very strongly with the local evaporation precipitation difference. So it doesn't coincide exactly because advection of currents can bring in lower or higher salinity water, reflecting a non-one-dimensional process. This slide shows the Gulf of snapshot of the FVCOM model. This is a model developed by Changshen Chen at UMass Dartmouth. It now runs a forecast for the northeast U.S. Through the Niraku system, and you see the website address above. So it's running 3-day forecasts. This is a snapshot for today, September 3rd, 2014, just to give you an idea of the model computed sea surface salinity in our region. And you can see that it varies from offshore around 35, off the shelf. So here we are off the shelf in deep water close to 4,000 meters. And we have inshore lower salinities in the low 30s. And that's a typical coastal water salinity, 30, 31, 32. And so there's a gradient in sea surface salinity as you get offshore. So inshore reflects two things. You have the Scotian Shelf freshwater that's coming into the Gulf of Maine, bringing relatively fresher water from the Arctic and the St. Lawrence River discharge. You have the rivers of the Gulf of Maine, such as the Penobscot here, Kennebec, dumping water into the Gulf of Maine, and those are more seasonal. They tend to dominate discharge in May, June, July, depending upon the timing of the snowmelt, but you also have large discharges around the times of storms. So that we see a reflection of that lower salinity water in the coastal regions of the Gulf of Maine. So here the range, and this was the range I put in, roughly 30 to 35. So if you go up these rivers, you will eventually reach 0. But in this range, most of the comprises most of the water of the Gulf of Maine. In terms of mean values in the ocean mean value is what we would consider high salinity compared to coastal water, 34.72 parts per thousand. And about 75% of all ocean water lies in this very narrow band between 34.5 and 35. So most of it is in that range, except near coasts or you have areas with very strong evaporation. The Pacific is a bit fresher than the Atlantic. And as I mentioned, there are these high salinity zones like the Red Sea, which can have up to 40 parts per thousand, and anomalous places like the Dead Sea or ancient seas that were once connected and then separated from the seas, and then the volume of water has decreased, essentially increasing the local concentration of salinity. Dead Sea has a very high salinity.